Hi friends, welcome to my channel Interesting Engineering. Today let's discuss about Kelvin's Double Bridge Method. So Kelvin's Double Bridge Method is a method of measuring resistance of extremely low value. This bridge method measures resistance even up to a lower value of about 0.001 ohms. And this method has a maximum accuracy of about 0.05 to 0.2 percentage. So this is the major advantage of using this method. So Kelvin's double bridge method is a method for measuring extremely low value of resistance even up to about 0.001 ohms, and it has a higher accuracy of about 0.05 to 0.2 percentage. So in our previous video, we have already discussed about Wheatstone bridge method of measuring resistance value, but in that Wheatstone bridge method, we had a certain drawback, that is the error due to contact and lead resistance. That is, in Wheatstone bridge circuit, we have 4 resistances connected in a bridge arrangement, and 2 arms have fixed resistances, and the other two among the other 2 arms, this is P resistance, Q resistance, R is the unknown resistance, and S is the standard resistance, and in between we have a galvanometer, and to this entire bridge arrangement we connect a voltage source. So this is the normal Wheatstone bridge circuit where we have 4 resistances P, Q, R and S, where R is the unknown resistance and S is the standard variable resistance. So this unknown resistance is measured in terms of the standard resistance under bridge balance condition, which is nothing but the bridge, the galvanometer, the current through the galvanometer is brought to 0. Under such condition, we make measurement by adjusting this variable resistor to measure this unknown value of resistance. But in this case, there is a problem of this lead resistances and the contact resistance. So this causes error in our measurement. So that error is being eliminated using this Kelvin double bridge method. And before entering into this Kelvin double bridge arrangement, let's discuss about Kelvin bridge arrangement, where to avoid this contact and lead resistance, we make use of a arrangement where this contact and leads are connected directly to this galvanometer, and the galvanometer point, this point D, is connected either to this position or either to this position, and we need to locate a point in between this point so that it is, the entire value is denoted by small r, and this small r should be the sum of R1 and R2. So we need to locate a point R such that it divides this entire lead value, entire lead resistance, to 2 equal halves R1 and R2 in such a way that the ratio of R1 and R2 is equal to P by Q, where P and Q are the standard fixed arm resistance of this bridge circuit. So we need to find a position R in such a way that it divides the lead resistance to two different positions R1 and R2. So in such a way that R1 and R2 is equal to the ratio of P and Q. Suppose if this point D is connected towards this unknown resistance side, capital R, this lead resistance, this point is connected, if this is connected in this position, then the unknown resistance, when we represent it in terms of the standard resistance, it will be the sum of the standard resistance as well as this entire position. So if this point, when this point D is connected in the position R1, our measurement will be the sum of S plus R1, so that the measured value will be very much greater than the actual value. Whereas if this point D is connected in position R2, the R2, when it is connected over here, the measured resistance will be the sum of R plus R2. So the measured value Rm will be very much greater than the actual value. So in both the cases, even if I connect either in R1 position or in R2 position, we have a erroneous measurement. So this erroneous measurement that we need to eliminate so that we could get a actual measured resistance. So in order to achieve that, we need to select a position R such that it divides the lead contact into certain portion R1 and R2 in such a way that the ratio of R1 and R2 is equal to P by Q. So how can we select it? Let's under balance condition, when we select a point R in such a way that it finds a ratio R1 and R2 is equal to P by Q, under balance bridge balance condition, the opposite impedances will be equal. So P into S plus R2 is equal to Q into R plus R1. So under bridge balance condition, when we place when we place this position D in a certain position such that it divides the lead contact into R1 and R2 in such a way that R1 and R2 is equal to P by Q. Under that condition, if the bridge is operated under balance condition, the ratio the product of opposite impedances are equal. So by means of which I have written this equation. So let's derive the resistance equation and find out whether the resistance equation have the effect of this R1 and R2. So for that purpose, we are going to derive an equation for this unknown resistance, and we are going to determine whether there is an effect of these lead resistances. So let me derive P into S plus R2 is equal to Q into R plus R1. This is under bridge balance condition. So during this bridge balance condition, let me derive the value of R1 and R2. So using this equation, I am going to derive the value of R1 and R2 in terms of P and Q using this equation. So let me first find out the value of R1. So for that purpose, in both these sides I am adding 1. So R1 by R2 plus 1 is equal to P by Q plus 1. So when we simplify, we get it as R1 plus R2 by R2 is equal to P plus Q by Q. So R1 plus R2 will be R. So R by R2 is equal to P plus Q by Q. So we can write R2 as, what is R2? When we cross multiply, we have it as Q by P plus Q into R. So this is R2. Let me derive for R1. So for that purpose, I am taking the inverse of this equation. So R2 by R1 equal to Q by P. So let's add 1 on both these sides. Q by P plus 1. So when we take LCM, we have it as R1 plus R2 by R1 equal to Q plus P by P. So R1 plus R2 will be R divided by R1 equal to Q plus P by P. So R1 will be equal to, when we cross multiply, P by P plus Q into R. So this is our R1 equation. So I have derived the values of R1 and R2 in terms of known values P and Q. Now let me substitute it over here. So P into S plus R2. Instead of R2, I am going to replace this equation here. So S plus R2 is Q by P plus Q into R is equal to Q into R plus, what is R1? R1 is nothing but P by P plus Q into R. So P by P plus Q into R. So let me simplify. P into S plus QP by P plus Q into R is equal to QR plus PQ by P plus Q into R. So in both the sides of this equal to sign, we have PQ by P plus Q into R. So we can cancel it out. So we have it as PS is equal to QR. So we need the value of unknown resistance R. So let me bring this Q to the other side. So R is equal to P by Q into S. So in our equation we have R is equal to P by Q into S. So this unknown resistance equation doesn't have any contact resistance terms. So by means of using this Kelvin bridge method, we have eliminated the value of this contact resistance in our unknown resistance term. But in this case, we don't know how to position this contact such that it have a exact ratio of R1 by R2 equal to P by Q. So for that purpose, we are going to make use of Kelvin double bridge method. So using this Kelvin double bridge method, we are going to eliminate the problem of finding out the exact location of R1 and R2. So the circuit for Kelvin double bridge will be, instead of a single bridge, we are going to make use of two bridge circuit. So the standard resistance PQ that we are going to make use of here, G. So this is our Kelvin double bridge circuit where we have standard resistance P and Q, and here we have a unknown resistance R, and here we have standard resistance S. So this is unknown resistance R and this is standard variable resistance S. So this is the resistive lead small r, and here we choose another two ratio arms small p and small q in such a way that P by Q is equal to small p by small q. We need to make use of two more ratio arms in such a way that the value of P by Q is equal to value of P by Q, capital P by Q. So this is our Kelvin double bridge circuit where we have two ratio arms, two set of ratio arms. One set have P and Q, these two are fixed resistance value, and one more ratio arm, that is small p and small q, and we select value of small p and small q in such a way that P by Q is equal to small p by Q, and here we have unknown resistance R, and this is the standard resistance, and this resistance is the contact resistance, and here I am going to name it as A, B, M, D and C. So this is our Kelvin double bridge circuit. So when we pass our supply voltage of E, when our supply voltage E is connected over here, the current I flows through the circuit. So the current I flows through these resistances. So let me derive the equation for Kelvin double bridge circuit. So when this bridge circuit is operated under balance condition, the current through the galvanometer is made 0. So at that time, the potential across these 2 points will be 0 under bridge balance condition. So under bridge balance condition, the potential across AB is equal to the potential across AMD. So the potential across these 2 points will be equal. So EAB is equal to EAMD. So here, what is EB? First let's derive what is EAB. EAB is nothing but, so this is 1 arm. So here we have open circuit here. So thus under bridge balance condition, this I into resistance P. So here we have EAC. So EAB equal to EAC into P by P plus Q. So under bridge balance condition, we are neglecting this part. So under balance condition, since this galvanometer current is 0, EAB is equal to EAC into P by P plus Q. That is, by means of voltage division rule, EAB is equal to EAC into P by P plus Q. Then let's find out the value of EAC. EAC. What is EAC? EAC is the current through this path. So in this path there are 3 resistances. So R, S and a parallel combination of this part. So the current I flows over here through one resistor, unknown resistor, variable resistor and a parallel combination of these resistances. So by means of calculating the current through these resistances, we can have EAC. So EAC is nothing but I into R plus S plus. So here this is the parallel combination P plus Q into R divided by P plus Q plus R. So P plus Q into R by P plus Q plus R. So this is EAC. So when we write EAB is equal to EAC into P by P plus Q. So P by P plus Q into I into R plus S plus P plus Q into R by P plus Q plus R. Then we shall find out the equation for EAMD. So here we need to find EAMD. So the potential across this point. So here we have the current through the R resistance and the current through the resistor small p. So that we can write it as I into R plus IAMD into small p. So IAMD is nothing but IMD. So EAMD is nothing but I into R plus IMD into P. So here what is IMD? IMD is nothing but the current through this path. So by means of current division rule, we can write it as small p into I into R by P plus Q plus R. So this is our second equation. So now let us equate these two, EAB equal to EMD. So I am equating this. So P by P plus Q into I into R plus S plus P plus Q into R by P plus Q plus R is equal to I into R plus PR by P plus Q plus R. So we have I on both sides, so I am cancelling it out, and then I am going to bring this P by P plus Q to the other side. So we have it as R plus S plus P plus Q into R by P plus Q plus R is equal to when we bring this P by P plus Q to the other side, we have P by P plus Q on the numerator and capital P on the denominator into R plus PR by P plus Q plus R. So the next step, I am going to divide this P plus Q by P, so it changes as 1 plus Q by P into R plus PR by P plus Q plus R. So here we have bracket, so multiply this into this, so R plus S plus P plus Q into R by P plus Q plus R is equal to R plus PR by P plus Q plus R is equal plus Q into R by P plus Q PR by P plus Q plus R. So we have R on both sides. Let me cancel it off. And then S plus PR by P plus Q plus R plus QR by P plus Q plus R is equal to PR by P plus Q plus R plus QR by P plus QPR by P plus Q plus R. So in both the sides we have PR by P plus Q plus R. I am cancelling it out and then bringing this QR to the other side. So we have it as S is equal to QR by P plus PR by P plus Q plus R here we have into 1 by P. So it will be, when we take this PR by P plus Q or Q plus R to the common outside, so we have it as Q by P minus, when we bring this to the other side, we have already taken PR by P plus Q plus R common outside, so the remaining term is Q, so we have it as Q by P. So we can write it as QR by P plus PR by P plus Q plus R into Q by P by, as we have said already, Q by P equal to small q by P. It's because of this equation, P by Q equal to P by Q. The same thing I have used here. So when we substitute this over here, we can have 0. So the remaining is S is equal to QR by P. We need the value of unknown resistance, so I am taking cross multiplying this, so it will be P by Q into S. So this is our unknown resistance equation. So we have it as R equal to P by Q into S, and here too we have eliminated the lead resistance small r. So by making use of Kelvin double bridge method, we can have unknown resistance in terms of known resistances. So this is our bridge balance equation. So by means of this Kelvin double bridge also, we have eliminated the lead resistance. So this is the major advantage of using this method. And let's summarize. This Kelvin double bridge method is a method for measuring low resistance value, and using this bridge method we can eliminate the error that that could occur in a Wheatstone bridge circuit, that is the error due to the lead resistance and contact resistance. So how to eliminate that lead resistance and contact resistance, that we have described using these derivations. So by means this is called Kelvin double bridge method because we have made use of two bridge circuit, that is two ratio arms are made use of in this circuit. So the ratio arms are obtained in such a way that the ratio of the ratio arms are equal. So by means of which we have derived this equation, R is equal to P by Q into S. So where R is the unknown resistance, P and Q are the two known ratio values, and S is the standard variable resistance value. So R is expressed in terms of standard resistance value. So this is about the Kelvin double bridge method. So in our next video we shall describe about ohm meters. So for more videos, keep watching. Please subscribe and share. Thanks for watching.